We looked at this heat transfer problem where we had the temperature cooling down. If we wanted to figure out the amount of heat radiating out, well, it depended on the temperature, which depended on the location. What we needed to evaluate at the end of the day was an integral with a bunch of constants, but most importantly, something that changed with x there. What happens if we didn't go through all that mechanics? Or what happens if we had some weird shape, and what we did is we put sensors on this. So we put a little temperature sensor, had a little infrared beam on this that could measure the temperature of the radiating heat, and we didn't actually have this function. What would change? I mean, this is entirely common in engineering, especially those people in mechanical who are doing the stress-strain diagrams, things like this, or stress-strain measuring tools. This is the kind of thing you do all the time, is you measure a bunch of stuff on different points, and then you try to add it up over the entire structure. So what do we have to do? We don't have to do much, but it's worth noting what does change when you have data instead of a function. When we have data, we have dots. That's all we got. We have a location, and we have some measurement, in this case here, of the temperature. How would we represent that? Well, we'd represent it as a vector x and a vector t. That's how we generate our plots usually. And that's pretty intuitive so far. What we're going to do is try to play with that and see what we can adapt or reconstitute, what we have to tweak when we have data instead of the function. We'll start with W74. And you should make sure that this other file is in your working directory, measured fin temperature.txt. And just so you see what that looks like, it is literally at location 0, the temperature is 100 degrees. At a little bit further down the thing, the temperature is 65 degrees, and so on. So 2 columns of data. We've loaded that kind of stuff before. There's where you actually read it in MATLAB. And we can run that. And there we go. There are our dots. We could make them bigger if we liked. So we can load in our data, and we have, at least in principle, the locations and temperatures of this function at various points. Only specific points, though, wherever we happen to measure. So what do we do with that afterwards? Which of these techniques would make some sense? If I have those dots, can I build rectangles out of those dots and find the area under the rectangles? Yes or no? Yes, absolutely. We can draw rectangles. Rectangle, rectangle. OK, so yes, check for that. How about trapezoidal rule? Could I connect those dots with straight lines all together? Yes, good. So in principle, we can do that. And last but not least, could we fit parabolas and find the area under a parabola? Absolutely. The only new one is quad. So think about it for a sec. Could I adaptively shrink the intervals and sort of hone in on where, if there were any, the discontinuities in the temperature? Yes or no? Good. Or mostly no's there. Fantastic. What's the problem? Why can't we use an adaptive method for this scenario? You don't have a function. Exactly. If you wanted to do something adaptive, you would have to say, oh, I need the temperature in the middle here. Well, guess what? Your buddy ran the experiment 3 weeks ago. They don't have a sensor on that point, and they're not going to have one anytime soon. So that idea of, oh, I can just move a little bit and find the temperature at some nearby place only works if you have a formula. If you have data, that is what you have. There is nothing else available. So here's where you get the trade-off. Quad is great if you have a formula. If you haven't got a formula, you can't adaptively move in and find new data points over what you've already measured. So quad's pretty much off the table. So that's why I think of this as you've got the finite methods of these 3 things here. Then you can go either down the quad route if you like, or if you have data, you pretty much have to go to fixed interval methods. There's nothing else you can do because that's how you measured your data in the first place.
So you're limited with those 3 to the number of data points.
Exact. That is an excellent point as well. And the n is determined by the data. We can't say, oh, that didn't get accurate enough. I want 200 intervals. Too late. You've only got 5 measurements. So it's much more constrained when you have data. Exactly. But that's the way it is. Sometimes you collect data, and that's what you got. So, and not to say that this puts limits on things. Well, it puts limits, but not necessarily fundamental problems, because people do this all the time with data. In fact, if you want a nice concrete example, if you think of the accelerometers in your phone, whatever other devices you've got, that's measuring acceleration. Guess what? When you integrate that, hey, I bet you'll use Simpson's rule to add up and find the velocity. If you're playing something that measures velocity or position on your phone and tracks position and velocity, it'll be using a data-driven Simpsons-based, Simpsons rule-based integral to get how far is my phone moved based on the acceleration data. Alrighty, so let's try to use what we had before. So we'll go to here. We'll notice that we had to have our function. Our function wasn't quite our temperature. It was our temperature times h times p. Temperature. Left-hand rule of f from 0 to L with, let's do a quick check. We can figure out how many points we have. There's 11. So there's 10 intervals. So if I was a naive waif doing this for the first time, I might think, hey, we spent a whole lot of time on Monday writing a left-hand rule function. Can we recycle that? I've got a function. It's temperature times the h times p. That's the math side. I've got an interval 0 to L. And I've got the number of intervals. Well, there's 10 intervals. I can't change that. So we run it. And it's going to start yelling at us. All right. Let's take a look at the left-hand rule code, actually. Another tip, if you have an error in a main program and the function that gets called by it, you can just click on the link, and it'll pop up the line and the file that the error occurred in. So what is the error? The error is complaining, attempted to access f bracket 0. F bracket 0. OK. Last time, f was a function. Can I say f bracket 0 if f is a function? Absolutely. What is the temperature at location x equals 0? What's the functions at x equals 0.5? We can put any number into a function. That's why this worked before. What is f now? It is not a function. Well, it's an array. Exactly. It's a vector. It's a matrix. So when I say matrix, look up the 0th element, is MATLAB happy or unhappy? It tells you in red, I'm very, very unhappy with you. You are doing things that I'm not allowed to do or that make no sense. And it's being perfectly reasonable because our function is not a function. Our function is now a sequence of data values. So you have to remember that f now is really equal to a vector of the f of xi's already calculated. In fact, it's saving us a bit of work because we don't need to know xi and stuff like that. We're not figuring out where am I. It's already done for us. We already have the function values. So in fact, it simplifies our code a little bit, but we're just going to have to tweak it. So what we're going to do is, why work with the worst thing? Let's work with Simpson and improve it or modify it to work with data. So Simpson's rule had this structure here. We had to find 3 x values, xi plus 1, xi plus 2, plug them into our function at 3 different points, at those points, and do some other 1, 4, 1, 2 delta x's, some other stuff like that. We're going to save this now as simp data, and we'll change the name to match. And just remind ourselves that f is equal to already f of x1, f of x2, f of x3, and so on. All right. So integral 0 is fine. Delta x, calculating it, is fine. Counting sounds good. Because we already have the function values, the only reason we needed the x's was to get the f values at those x's. That's already taken care of for us because someone else measured it at the various x values, so gone. What's the only thing we have to do here? Before x was a real number, it was 0, 0.5, 0.75. Now it's, well, no, I want the first function value and the second and the third. Those are the heights of the 3 data points. Bring that up here. I want to know how I'm going to connect this point up here and that point and that point. So that's f bracket 1 if it's a vector, f bracket 2, and f bracket 3. So in fact, we get this even simpler. We just take out the x's. And here I want the next f value, and then I want the one after that. It is unfortunate, it is really deeply unfortunate that MATLAB has this almost identical syntax for functions and vectors. A lot of languages don't have that. Because this looks like it's almost the same thing, and you really have to think, how is the computer reasoning with this? If f is a vector, I put in 1s, 2s, and 3s and say, what's the first, second, and third thing in my vector? That's what I got now. First, second, and third, and then the next time it'll be the third, fourth, and fifth. This will work fine, but you have to know that f is a vector. If it's not a vector, this will also barf, so you can't mix and match the data and the function-based versions of this. But that's OK, because we called it simp data. So it'll be obvious which one we're going to use. So let's go down here. And now we're going to try using simp data on this and see what happens. Knock on wood. It works. Fantastic. And notice it also gives us a value that's close to the exact value. No, that's not the right integral value, sorry. Integral value is 2.36. And we get 2.361. Can we improve on that? Can we do better? They're not that close in alignment. Could we use more intervals? That's what fixed it last time. No. We got the data we got, exactly. Someone went out to the field. They only collected 11 data points. But it's good, right? This is pretty close to the real thing. And at some point, someone made the decision, I'm willing to spend enough money to collect 11 data points. The consequence of that is that my answer will not be super accurate. There it is. That's the trade-off you make when you do measurements in the field. What you can derive from them is subsequently limited. But that's it. That's how we can apply Simpson's rule to data. And the only change, really, is the syntax of what f bracket something means. If it's a vector, you have to think it has to be numbers like 1, 2, 3. If f is a function, you can plug in x values. And x values can be whatever you want, minus 23.7 or 17.9. The key thing is to recognize when you're doing it wrong and recognize what the error message is telling you. That attempted to access f bracket 0 tells you exactly where the problem is. I'm using f. I'm putting the number 0 into it. Why is that crazy, or why does MATLAB think that's crazy? Well, because f was a function, worked fine. Now it's a vector, doesn't work fine. Fix your code so it matches what your inputs are giving it.